This is problem 16100. It's on page 749. A 16-pound uniform disc is attached to the 9-pound cylinder rod AB by means of frictionless pins at B and C. The assembly rotates in a vertical plane under the combined effect of gravity and of a couple M, which is applied to rod AB. Knowing that at the instant shown the assembly has an angular velocity of 6 radians per second and an angular acceleration of 15 radians per second squared, both counterclockwise, determine A, the couple M, and B, the force exerted by pin C on member AB. All right, so what have we been given here? Let's make a diagram. Now let's see. There's a rod that's pivoted on the ceiling. The rod has some size. It's very slender. I'm going to have trouble drawing the slot. But let me try. Let's see, so let me make a decent size wheel here centered, so we'll like that. There we go. Not a very good wheel, but there it is. There is a slot, and I'm going to cheat just a little bit and move that line over so you can see the slot. So there's the slot, and there's a pin in the slot, and that pin is passing through the wheel. It's connecting to the wheel. We'll call that point C. We'll call the center of the wheel where it's pinned to the slender rod, we'll call that point B. Now the distance between the pivot point on ground, which we'll call A, and point B, that distance is 20 inches. And the distance between B and C right here, that's just 6 inches. The radius of the wheel, called R, is, in fact I'll use a capital R, you'll see why in a moment. That's 8 inches. And the wheel has a mass, I'll call it M sub W, of 16 pound mass. The slender rod, which we're assuming is uniform, despite the fact that there's a slot taken out of it. By the way, that's a 30-degree angle if you're wondering what I'm drawing now to the center of it. 30 degrees. Anyway, the mass of this rod is 9 pounds of mass. Let me call it M sub R equals 9 pound mass, the mass of the rod. Now, at this instant shown, the angular speed is 6 radians per second clockwise. It's going this way. No, clockwise. That's the other way. Yeah, falling down. And the angular acceleration, no, I'm wrong. It is counterclockwise. It's not clockwise. Counterclockwise. I said that, so it is going counterclockwise. It's swinging up. The angular acceleration is 15 radians per second squared, also counterclockwise, and I have forgotten to draw the moment M that acts on this assembly as well. So we're supposed to find the magnitude of the moment M required to make this, at least this acceleration as it is, and then the force between the pin and wheel B. So the force of the pin on B, or B on the pin, however you want to look at it. So let's start off with a free body diagram of the rod and the wheel together. Now understand the rod and the wheel, although they are separate bodies, they are together, right? They can't move relative to one another. Of course, they are separate bodies, so I'll treat them as separate weights. The weight of the rod, the weight of the wheel. Of course, there's a moment acting. It's not mass, that's the moment that's acting on it. And there's also reactions. Now, I'm going to rotate my coordinate system. Obviously, the weight acts straight down, but I want to write this as AX and AY. Because I want to deal with this with a rotated coordinate system XY like this, where the angle here is theta, or you could look at it as the angle here is theta to 30 degrees. Now this free body diagram, or the effect of all these forces and moments, has to be to cause dynamic forces and moments on the rod wheel assembly. Again, treating these two as separate, there would be an I of the wheel alpha an angular dynamic moment, and an I alpha of the rod together. Now, I'm not combining these two in the sense that I'm combining their moments of inertia. That can be done, but you haven't learned how to do it yet. So I'm just treating them separately because it doesn't matter at what point I consider this moment to be applied, just like it doesn't matter at what point M is applied. It's just a counterclockwise moment. You'll have the same effect no matter where it's applied on the body. Now, the center of gravity of the rod is halfway down its length or so. So I'm going to write MR ARX and mass of rod, acceleration of rod in the y direction up there. And then I'll write mass of wheel, acceleration of wheel in the x direction, and mass of wheel, acceleration of wheel in the y direction. So there are all the dynamic forces, dynamic moments from the, or on the kinetic diagram. Now, a little bit of kinematics is in order here. There is a relationship between the x components of acceleration and the angular acceleration of the whole assembly. As a matter of fact, it's pretty easy to see that ARX is equal to L over 2 alpha, and AYX, I guess I shouldn't write it that way, ARX equals L over 2 alpha, and AWX equals L alpha. So now we've got an expression in terms of alpha for all of the accelerations. So now let's sum moments about point A. Well, why would I choose point A? Point A is not the center of mass. If I were to choose to sum moments about the center of mass of the rod, well, I'd have AX in the moment equation. I'd have a dynamic force. There's no way I can get rid of all the dynamic forces, so I may as well sum moments about point A and just include the dynamic forces on the right-hand side of the equation. So in that case, I would have obviously the moment applied M, don't forget that one. But there's also the moment of the forces. So WR causes a moment, and its moment arm would be L over 2 multiplied, well really it's just this distance, isn't it? Right? Just that horizontal distance directly below A. So what is that distance? Well, this side is L over 2, right? So the bottom down here would be L over 2 sine theta. So L over 2 sine theta. Similarly, the moment arm for W, the weight of the wheel, W sub W, that would be W sub W L sine theta. Now notice that both of these cause negative moments about A. So that's all the moments on the left-hand side of the forces and the direct moments that are applied. On the right-hand side, the easy ones to write are just IR alpha plus IW alpha. That's obvious. But there's also the moment of the dynamic forces. Now, the dynamic forces in the y direction pass right through A, so we won't include those. That was actually the whole reason for rotating the coordinate system. But the dynamic forces MW, AWX, and MR, ARX do cause dynamic moments. And so we have to write plus, for the first one, MR, ARX times L over 2, but not all of it, right? No, it is all of it. Yeah, all of it, L over 2 times that. So that's that. Plus, let's see, MW, AWX times L. Okay. Now, we were asked to solve for the moment itself, M. What moment is required to make this action? So let's solve for it. We just move these terms to the other side. We have, let's try again. W sub R sine theta L over 2 plus W sub W sine theta L over 2. No, not L over 2. That's just got an L. Sorry. There. Plus IR plus IW times alpha. Continuing over here, let's see. I want to get rid of ARX. ARX is just, let's see, L over 2 alpha. And I want to get rid of AWX, so that's just L alpha. So let me write them that way. So plus MR. ARX is L over 2 alpha. And then this L over 2 comes from there, see? So this whole piece here came from ARX. For the next term, we have plus mass of the wheel. AWX is L alpha, and then L, see that L came from there, and that whole thing, L alpha, came from AWX. Okay? Now, IR and IW, we can go off and compute off to the side. I guess I can do it down here. IR for the rod is going to be the mass of the rod times the total length of the rod squared divided by 12, because it's a long cylinder rod. IW for the wheel, since we're assuming that it's a flat disc, would be 1/2 the mass of the wheel times the radius of the wheel squared, and I need a capital R. The reason I use a capital R is because I've got a lot of subscripts R running around, and subscript R means the rod, so I needed to use a capital R for the wheel. I guess I could have used C for the wheel, but we've got a point C, so that may have been confusing as well. So that's why I chose a capital R for the radius, just to make it clear. So now I've got expressions for these two terms, and I can make the substitution. So let's see, what else can I do? So the moment equals WR L over 2 plus WW L. I guess we could factor out an L. How about if we have WR over 2? And then we'd be left with what? An L sine theta, right? Yeah. So that simplifies those. Plus IR. Well, IR is, let's see, MR L squared by 12. IW is 1/2, or let's just say MW capital R squared over 2, and then times alpha. Let's see, plus MR L squared by 4 alpha plus MW L squared alpha. Okay? Well, let's see. We've got an MR L squared alpha and an MR L squared alpha. Here we've got a quarter, here we've got a 12. So let's rewrite it, WR over 2 plus WW L sine theta, and then we'd have plus, like I said, if we combine these two, all we've got to do is add a 12th to a 4th. Well, a 4th is 3 12ths, so 4 12ths, which is a third, so MRL squared over 3 is a third. And here we've got MWR squared over 2. Do I want to combine that? I guess I could. So plus MW. Now we have what? R squared over 2 plus L squared. And then all this is multiplied by alpha. All right, now notice that we have all this, right? We have, well, I mean, we've got the mass, but we can calculate the weight trivially. That's very easy. We've got MR, the mass of the wheel as well. We've got the radius, we've got L. Yeah, we're ready to go because we've got the angular acceleration. So let me get rid of the free body diagrams. I think we're done with them. We really only needed a moment equation. And in fact, I'll just use the last one. So the moment equals, let's say we need the weight of that. That would be 9 pounds force. So over 2 plus the weight of the wheel, which is 16. Now understand, I am writing pounds force. 9 pounds mass will weigh 9 pounds force on Earth. That doesn't mean that 9 pounds mass is 9 pounds force. 9 pounds mass is mass, 9 pounds force is force. 9 pounds force is the effect of the Earth pulling on that 9 pound mass, okay? I just pulled the thing out because the equation calls for weight. Now I need to multiply by L, the length of the rod, which is 20 inches, and sine of, no, it's not 18 degrees, this is 30 degrees. I was thinking of another problem. So that takes care of this first term. That all is done. Because I'm running out of space, I'm going to go to the next line and write plus the quantity of MR, the mass of the rod. Now that is 9 pounds mass. You can't write 9 pounds force here because the equation calls for mass. Let's see, then we need times length squared. Well, that's 20 inches. The square works on the number and the unit. Divided by 3, that takes care of that term. Of course, we're going to put alpha out at the end. Plus the mass of the wheel. Now, the mass of the wheel is 16 pounds mass, not 16 pounds force. Multiplied by r squared over 2. Well, r squared, that's going to be 8 inches quantity squared divided by 2 plus 20 inches quantity squared. Takes care of L squared. In the parenthesis, and then alpha is 15 radians per second squared. That's a counterclockwise or a positive direction, so I plug it in as positive. And what do we have? Well, let's see, we've got pounds mass inches squared per second squared. But in the first term, we have pounds force inches, so these two don't jive, right? When you see that you have pounds mass and you wish you had pound force, you can't convert pound mass to pound force, but you can convert pound mass to pound force per foot per second squared. That you can do. So that's what I'm going to do here. As a matter of fact, since I'm out of space, I'm going to divide this whole term by 32.2 pound mass foot per second squared per 1 pound force. You see, the pounds mass go away, but I'm converting to pounds force per foot per second squared. Okay? Now, the inches squared don't match with the feet I've got here, and the feet don't match with the inches I have there. I'm going to leave this in pounds force inches. So I'm going to leave the inches alone. I'm going to get rid of the feet. So 12 inches are 1 foot. And now one of the inch sets will cancel, and we'll just have pounds force inches for both terms. It's a mess, but when you plug it all into your calculator, you find that the moment required is about 519.91 inch pounds force. And that's the magnitude of the moment. Now, that's not the only story, right? That's not all of it. That was just part A. What about part B? Notice we have no way to calculate the force between the pin C and the rod R. There's no way to do that, right? Because the free body diagram I took was the rod with the wheel together. I need a new free body diagram. Here's an easy one to take. Just take the wheel. If we take the wheel as our free body, what forces act on it? Well, at point C, there are potentially Cy and Cx forces. There's the weight of the wheel. And at B, there are Bx and, let me put it down here, well, it's also up, By forces. Okay, that's not very good. Let me take that off the wheel. There we go. Now, Cy has to be 0 because this is just a pin and slot, so there can't be any force in that direction. So let me just erase that. You could have just crossed through and said 0, but logically, since that's a pin and slot, it has to be 0. Now, this is equal to the kinetic diagram, which would look like this. We've got our wheel. We've got the mass of the wheel, acceleration of the wheel in the x direction, mass of the wheel, acceleration of the wheel in the y direction, and the inertia moment, or the mass moment inertia of the wheel, times the angular acceleration of the wheel. Okay? Well, if we sum moments about B, that'll get rid of Bx and By. Of course, summing moments about C would get rid of By, but I want to sum moments about B because at least it'll get rid of the weight of the wheel as well and simplify my equation. So summing moments, let's see, I guess I need to separate these two. Summing moments about B, counterclockwise positive. Well, let's see, Cx causes a negative moment, so it would be minus Cx, and I didn't really, I know it's 6 inches between B and C. I didn't give it its own symbol. Let me just write the distance between CB, okay? Because that is the moment arm of the force Cx. Anyway, that is equal to I of the wheel alpha. So solving for Cx, which is the question really, right? Because the question is how much force is between the pin and the wheel. That's Fc on B or B on C. Then that is equal to, let's see, let's put the negative sign on the other side, IW alpha divided by distance between CB. IW is, of course, mass of the wheel, radius squared by 2. And so now I can calculate Cx. Let's see, so that'd be negative mass of wheel, 16 pound mass, Okay? Notice I can't put force in here. I know we want to get force out. I cannot put force in there. The equation calls for mass. So 16-pound mass times the radius of the wheel, 8 inches quantity squared. Alpha is, where is that? 15 radians per second squared, divided by CB, the distance between the two, 6 inches. Now one of these inches will cancel with one of these. So right now what I have, radians go away for free, is pounds mass inch per second squared. But that's not what I want. I like pounds force. So what I will have to do is multiply by, let's see, 32.2 pound mass foot per second squared per pound force. The pound mass are gone, but now I've got an inches and foot problem. So let's see, 12 inches per foot takes care of the feet. And let's see, now I've got inches squared here, which cancels with inches squared there. And all we're left with is pounds force. So since pounds force is in the denominator of the denominator, it's really in the numerator. So plug all this into your calculator and you'll find that this is about negative 3.313 pounds force. So that's CX. In other words, I assume that CX is in the wrong direction. CX really is acting in the lower direction. So that's it. You'll notice that the angular speed didn't come into play. They just gave us that probably to confuse us. There would be a normal acceleration of all these points because of this angular acceleration. The magnitude of that normal acceleration would be omega squared times whatever distance there is between the pivot point at A and whatever point you take, whether it's C or B.